All right, so welcome back. Rational functions and rates of change, a topic that just keeps coming back at you in advanced functions. And that's all right. Sometimes the more that we do it, the more acquainted we get to it. I hope that at some point you're going to say, okay, I understand. Okay, so we have an average rates of change, which typically relate back to some kind of a secant, as you have shown here on the quadratic. So some parabola here in the blue, and then I drew a secant, okay, connecting the 2 points, and then we can find the rate of change that way. It's more of an average rate of change, okay, over an interval. And then, you also were starting to think about and talk about kind of tangents, right, at a particular point of a function, and that started to intertwine the instantaneous rates of change that you would have. And those instantaneous rates of change, we kind of defined in this way. So if you wanted to find it at a particular point, A, you would substitute it in, okay, you adjust, okay, so you have this little h, okay, and that h is being, it's a very, very tiny, small number, so this h tends towards 0, okay, and then you can find the instantaneous rate of change at a particular point. So that's nothing new, right? Again, so instantaneous rates of change, if you like, I'll put up a link up above there, if you want to see some previous examples. Our idea within here is, because we're studying rational functions, right, do these things apply? And the answer is yes, of course they do apply. Now, the only thing is, when you are dealing with rational functions with some polynomial on top and then something at the bottom, but even if there were not polynomials in the numerator and denominator, okay, you always have to be careful with rational functions because, you have undefined criteria. If you take the denominator and you set it to 0, you get some 0. So we get undefined results. So our domain is not full, and sometimes, we'll get kind of vertical asymptotes that we never really reach. Okay, and then you also have the concept of holes, right? So sometimes that may happen, and again, you're not going to have an instantaneous rate of change defined at these particular points, okay, where it's a hole, or if there's like a vertical asymptote of some kind where the functions are just not defined at those points. So that's really the only thing you have to be careful. Now, for holes and asymptotes, both vertical and horizontal, okay, and then slant ones, okay, I'll put up a link up above there because we went over that, all right? So now, with respect to these rational functions, let's do a little bit of a kind of a review through just one example. I'm not going to really do much more because you have done these rates of change now over and over. In fact, there was a chapter on it. And then in advanced functions, what happens is you just keep bringing the concept back, okay? So that it just keeps ingraining in your mind. You do it kind of chapter by chapter. And then you eventually okay, I'm understanding these rates of change, what's happening, the instantaneous rate of change, the tangent at a particular point, how it was related to the rate of change, and so on. All right, so here's an example of a rational function, and I just want to show you, because this rational function on purpose, I made it so that it has both a hole and it has vertical asymptotes, okay, that we can't really define. So then I can talk about, where can we find these rates of change, and then maybe we'll do one of them at a particular point, and you'll see, not a big deal. It's exactly the same concept that you had before, okay? So first of all, if we take this, we obviously typically want to be able to define our domains or maybe our ranges if there are no restrictions. And for rational functions, we can certainly sketch them. We have the tools to find out, what the holes are, what the vertical asymptotes are, what the horizontal asymptotes are, and so on. So we know quite a bit about these, right, from previous work. So now, if I break this one down, which I will, okay, so I'll take this, so x minus 1, and then in the denominator, I'm going to try to factor this. It's not always factorable, but I want to factor it because I want to find all my kind of quirks in this particular function. X squared plus x, I guess, so what do we have here? This is going to be x. This is plus, so I have a minus 2 in here. So this is just a quadratic, so I'm just factoring it out in terms of the rules we had for quadratics. This is going to be, I guess it's going to be plus 2 and x minus 1, right? So x squared, yeah. Okay, so that's my factored form. Okay, so that's what I would have here. And now, okay, so right away I notice. So here notice we have x minus 1 and x minus 1. So whenever this happens, we know that we have a hole in our function at that point. So it looks like what we will have here from right there at x is equal to 1, okay, we have a hole. Okay, so it's not going to be defined at this point, but we have a 0. And, okay, so in the numerator, and we have a 0 in the denominator, so that gives us a hole. Now, from right here, so from this, okay, it looks like we're going to have a vertical asymptote at x is equal to minus, I guess, 2. All right, so that's what we're going to have there. Okay, moreover, okay, so let's take a look, okay, our horizontal asymptotes that we have in here. And so for this one, you know, as x tends towards infinity, okay, so what we're going to be getting is, actually this is going to tend towards 0. Okay, so you have, if you have a very big number x, but you have x squared, okay, in the denominator. Remember, if the degree in the denominator is bigger, okay, then in the numerator, then it's going to tend towards 0. So that's what we have, and that's going to happen from both sides. Okay, on the negative side, if you put it into negative infinity, okay, it's fine, you know, so we have that. So within here, our problem, if we were trying to find, okay, these rates of change. Now, if you're doing just a regular secant, okay, between 2 points, fine. Just be careful so that you're not crossing over, okay, these vertical asymptotes, you know, where 1 point, so let's say if our vertical asymptote is at x is equal to negative 2, you know, if you wanted to find, okay, what the average is between, let's say, the point negative, okay, 3, and then, you know, let's say plus 2 or something like that, you know you're going to be crossing through that vertical asymptote. So just be careful, because technically, you know, if you're trying to find an average of the rates of change between those, okay, so between these, then, you know, you are going to run into the problem where at negative 2 it's undefined, okay? So you can find the secant and you can continue doing this, okay? So you can define these, but just make sure that it's on intervals that kind of don't really cross through, okay, these vertical asymptotes. Now, technically, you can still find it, right? You can still find what the secant is, because it's just basically a line between one point and another. So it will exist, okay? All I'm saying is that at this particular point, okay, we can't have a rate of change at negative 2 because it's not even in the domain of this function. And the same thing, okay, we cannot have a rate of change exactly at x is equal to 1. At that particular point, it's a hole, and it's undefined for this function. So again, it doesn't really exist, okay, for those two particular points. All right, so let's try it, okay? I am going to try to find the secant between here. If I'm really just connecting these, not a big deal, okay? So I can certainly try to find that. And then let's try to find some instantaneous rate of change at a particular point, and you'll see that it's nothing else than what we have done previously in all of these different rates of change, okay, that we had. All right, so here we go. So I'm going to take, so let's say I want to find, okay, so my secant point, so this is going to be at f, okay, and let's say this was 2 minus at f, okay, minus 3 all over, okay, and this is going to be, okay, 2 minus, I guess, negative 3, right? So I'm really just finding, I mean, this is just the slope, right? So that would have been the secant line between those, and just because it's a rational function, okay, no big deal. So I'm going to substitute these back in, okay? So the f at 2 and then f at negative 3, I'm going to find out what those are so that I can find exactly, okay, the rate of change, the average rate of change, or the secant in between those two particular points, okay? So I'll do that in fast forward fashion. All right, so here you go. So it's 1 over 4, okay? So that would have been the actual slope, okay? between those two particular points. And that is just utilizing, again, so right here, it's all I'm doing. Okay, we have substituted. Okay, so this was 2. Okay, and this was -3. And so this is 2 minus -3. And then we found out what the actual answer to that would be. Okay, so we've found this secant line right here. Now, of course, it's not from this graph. Okay, we'll graph it shortly on this item. Okay, in terms of Desmos. So I'm going to actually take out Desmos and we're going to graph this whole thing. Okay, to see it. We could sketch it, so that's for sure. We can do that. But let's utilize Desmos. And then, you know, we can see that between those 2 points, okay, what the actual, that secant line would have been. Okay, so, okay, all right. So here's Desmos. And so if I punch this in here, it's going to be x minus 1 all over. So this is x squared plus x minus 2. Okay, so here you go. So as you can see there, okay, so at -2, we have our vertical asymptote. Notice the horizontal ones is basically at 0. We're supposed to have a hole at 1, you know, so this is, where's 1 right here? Yep, there we go. It's undefined, okay, as you can see it. So there's a hole right there. And now if I plotted, okay, so the points, okay, so here is my first point. So that one was, f at, let's plot these points. This is, 2 and f at 2. So we can plot that point there. And then I can plot the other one, -3 and f at -3. So that's the other point. So there you have it. All right. And now if you can see, so the secant line in between those points, okay, so connecting them through, and we could find the y-intercept if we wanted, okay, but notice that if we would connect those 2 points together, okay, you know, you would have a secant line, but it does cross through the undefined. But that secant line is still there that we would have. So now, what if we wanted to find, okay, let's say the instantaneous rate of change, and we wanted to find the instantaneous rate of change, let's say at 2, all right? So now notice at 2, so that function, because it is going to be, so notice that the slope, if you put a tangent line, it's going to be negative, and it doesn't look like it's going to be very steep, so it's going to be a very small one. And that, for rational functions, you do exactly the same way. So if I would want to find, okay, so if I take this function, and then I want to work with the, so let's say we set 2, right? So that's what we want to be able to find. So that's my A, all right? So for this one, okay, so what we have is, we have the following. So we have the point, okay, this is going to be 2, you know, plus our little h, okay, that h is supposed to be very tiny, and then at 2, okay, so we want to be able to find, okay, at those 2 particular points, what they are. So if I want to do that, so this is f2 plus h minus f at 2 divided by, it's going to be divided by h. And now whatever h might be, and h is going to be very small. So let me try to simplify this. Let's see what we get. It's supposed to be negative and small in terms of my tangent line. So I'm not going to substitute anything for h yet. Okay, I'll try to see if I can manipulate this through. All right, so here you go. So I manipulated it. I mean, it's not bad because of the fact that you had that hole. So you know, this cancels out. So really our function is kind of this on at 2. And now substituting it all back in. So I manipulate it so we get this. So now notice, if h gets, you know, really, really, really tiny, it looks like my slope is going to be -1/16, and this is at 2. So that's my instantaneous rate of change, okay, that I have. And notice it is negative. That's what we kind of predicted through the graph at that point, right? So it's definitely that. It's negative and it's very tiny, and in this case it's 1/16. So this is really just kind of a deja vu. So I'm not really trying to provide you huge amounts of information. It is more with regards to, you know, looking at this concept of rates of change again and understanding that it's no different for rational functions. You can still do all the things that you want to do. The only thing is, please remember that at the points where your function is not defined, so at vertical asymptotes and you're at holes for rational functions, then you can't really find any instantaneous rates of change at those points, all right? So that's something just to keep in mind, because that didn't happen in polynomials, for example, you know, because they were very nicely behaved and we didn't have these asymptotes that were vertical, and we didn't have any holes. So in here, you do have that, and be careful with it. So if your teachers give you that at, you know, find the instantaneous rate, let's say for this function, if they said at -2, you would have to say, well, it's undefined. It doesn't really exist because there's a vertical asymptote. And the same thing would happen at x is equal to 1 because there's a hole. All right. So that's all that I'm going to say for this particular video. I hope that you find this useful as you're going along. The goal is always, you know, try to watch the videos, okay, in order, and then you'll have a good sense of what's coming at you in this advanced functions course. All right, thanks for watching. We'll see you in a future video. Bye, everybody.